he yesterday expressed about the FRT gravity on a modified gravity. And the Starobinsky lecture. So if you go for the Starobinsky model, so the Starobinsky model is very famous for the R square model. So f of R square, which is also a modified gravity approach. So today what I will do, I will go for a FQLM gravity. So this is a gravity which was proposed by us. The baby is not born till today because it is the paper we submitted the second revision December 10 to JCAP. So it is still under review. So the baby yet to born, and we are hoping to get this baby in next year. So I welcome all the suggestions because still the paper is under review. Okay, so the outline of my talk will be like this. I will go for the introduction of the gravity, but most of you already discussed last 2 days. Then why we are going for the modified gravity. Then I will discuss the types of geometry, what Dawood expressed and Saintan asked about the torsion and the non-metricity. So that basically the geometric trinity of the general relativity. So that I will go for the types of geometry here. After that, I will come to the proposed FQLM gravity, then what about its implications. Okay, so the first question is, what is gravity? So from our childhood, we started the gravity with the falling of the apple. The falling of the apple story by Newton, that is what the starting point of the gravity for everyone. Then coming to Einstein. So Einstein's gravity basically based upon the Riemannian curvature tensor with the famous field equation which he proposed in November 1915, that the left hand side is the geometry and the right hand side is the matter, and based upon the metric he has discussed the action principle. Now these are the observational times. So basically the success of general relativity, which already last 2 days it was discussed, the bending of light, then coming to the Persian mercury, gravitational lensing, gravitational waves, and time dilation. So all last 2 days the talks already discussed about it because they are based upon the GR. Then coming to Einstein. So what is the basically problems in Einstein's general theory of relativity? Why there is a need of new gravity or the modifications of GR? So the dark matter problem, then coming to the cosmic acceleration, and the present cosmological tension, that is particularly H0 and S8 tensions, then quantum gravity, and the singularity problems in general relativity. So based upon these problems, there are various modified gravities proposed from time to time, starting with FR gravity, then Orensky gravity, FT gravity, FQ gravity, and so on. Okay. So if you go for general theory of relativity, basically Einstein's general theory of relativity, which is based upon the Riemannian geometry. So basically the Riemannian curvature geometry, the extension of, so we started with Euclidean geometry, then the need of the Riemannian geometry. So based upon the Riemannian geometry, there is general theory of relativity. Then the extension is f of r, the function of Ricci scala. So the f of r gravity. Then from f of r, there is a coupling gravity known as f of RLM gravity, where LM stands for the matter Lagrangian. Then another one is the f of RT gravity. So T is the trace of the energy momentum tensor. Then f of R phi gravity, where phi is the scalar field. Then f of RT, R mu nu, T mu nu. So starting from FR, these are the extensions of f of R or the coupling gravity. Some are the minimal coupling and some are the non-minimal coupling gravity. So the coupling are based upon the matter Lagrangian LM, then the trace of the energy momentum tensor T, and the scalar field phi. Okay, so these are the extensions based upon the Riemannian geometry starting from general relativity. Now the question is the only geometry which can express the gravity, the Riemannian geometry, or there is any other geometry which can express the gravity? So coming to Weyl geometry. So when Weyl developed the Weyl geometry, then Einstein used the Weyl geometry, the unification of GR and the electromagnetism. So once the Weyl geometry came to the picture, the main question came the affine connection. The affine connection was not used earlier because Einstein's theory based upon the metric. So then this is the question of the affine connection. So coming to the affine connection here, this is the generalized form. So the affine connection contains 3 terms. The first one is the curvature term or the second order Christoffel symbol, which we are used in GR. Then the second one is the torsion, which is known as the contortion tensor, and the third one is the non-metricity. So affine connection has three terms which we use to tell the trinity of geometry in general relativity. So one can go through this Lavinia-Heisenberg's review, which is published this year in physics reports. One can get all the details of the geometry in that review article. Okay, so here this describes the Riemannian tensor, then the contortion describes the teleparallel gravity, and the non-metricity or the deformation tensor describes the symmetric teleparallel gravity. So based upon these three, we have three gravity, which is f of r, f of t, and f of q. And then you can go for the couplings in r, t, and q gravity. So you can get various minimal and non-minimal coupling with respect to this trace, then matter-Lagrangian, and the third one is the scalar field. So what we did in this article, so we proposed a coupling with the q and the matter-Lagrangian Lm. Okay, so coming to general relativity, so the RTQ. So in general relativity, this R, which is non-zero, and the torsion and the non-metricity both are 0. Then coming to symmetric teleparallel gravity, so in teleparallel gravity, the torsion tensor is not 0, whereas the Riemannian curvature tensor is 0 and the symmetric tensor is also 0. And coming to symmetric teleparallel gravity, the non-metricity Q is not 0, whereas this torsion and the Riemannian curvature tensor both are 0. So these three are known as the trinity of the geometry in general relativity. So based upon this trinity, we used all the modified theories of gravity. Now what about the base on that? So coming to this curvature, torsion, and non-metricity. So when you go for the curvature, so which is used in general theory of relativity, particularly this Riemannian curvature tensor. So here the direction of the vector changes when it is parallel transport. But coming to the teleparallel equivalent, this torsion based, so the non-closure of the parallelogram. So when you go for this parallelogram, the non-closure of this parallelogram during the parallel transport is attributed to the torsion. And coming to the symmetric teleparallel gravity, the non-metricity. So here the length of the vector changes as it parallel transports. So in parallel transport, the length of the vector changes in the symmetric teleparallel gravity. So this is the base of these three gravity based upon R, T, and Q. Okay, so coming to the new proposal, which we started, actually we started last December, this gravity, and submitted to JCAP, and we submitted this December the second revision. Okay, so this paper is available in archive. So the action with for this FQLM gravity is a coupling of Q and LM, where Q is the non-metricity and LM is the matter-Lagrangian. Then coming to the field equation, so we derive the field equation here, and the FQ and FLM, which is the derivative with respect to Q and LM, is used here, and this is the superpotential. Now coming to the Einstein tensor form. So in Einstein tensor form, this is Gij plus half Gi. So this is the field equation, and the FQLM Klein-Jordan equation also we derived in this, taking the scalar field, we derived the Klein-Jordan equation in this article, and we also studied the mass of this effective and the taking with scalar field particle. So another thing is what we did, so this FQLM gravity can be reduced to general theory of relativity, and also this can reduce to FQ gravity. So when you make this for minus Q plus 2Lm, then we get the Einstein's field equation general theory of relativity, and if you make this Q as a function of Q plus 2Lm, then this FQLM will reduce to the FQ gravity. So one can reduce this FQLM gravity to general theory of relativity and also FQ gravity. Okay, so coming to the energy momentum tensor, because if you go for the conservation equation, mostly the conservation equation fails in all the coupling gravity. If you go for FRT gravity, FQT gravity, or you go for any coupling gravity, in most of the coupling gravity, the conservation of the energy momentum tensor fails. So here we have taken the energy momentum tensor with the balance equation, which is given here, and in the hypermomentum density we used, and what we did here, we calculated this dynamics of the massive particles and the tensorial form we checked. So once we get the form, if it is 0, then it is conserved, and if this equation is not 0, then it is not conserved and the energy transfers. So this is basically the energy balance equation. Okay, so coming to the Friedman equations. So the Friedman equations in this FQLM gravity, starting with a FRW metric and the energy momentum tensor of this form of a perfect fluid. So this is the first generalized Friedman equation, and this is the second generalized Friedman equation in FQLM gravity. Then coming to GR again, so these are the two Friedman equations, so one with effective density and another with effective pressure, and these two, and this is the conservation equation. Then the same thing, we generalize these two terms in the first Friedman and second Friedman in FQLM gravity. And so going for this gamma, so this gamma is the basically the conserved, so whether it is conserved or unconserved. So if coming this balance equation, so if this gamma is greater than 0, then the energy particles are increases, and if the gamma is less than 0, then the particle decay due to the coupling. And if you make this gamma is 0, then the conservation equation satisfied. So it is the energy conservation equation. Then coming to the deceleration parameter, which tells about the acceleration or deceleration of the model, the deceleration parameter Q is given in this equation for this FQLM gravity. Okay, so what we did here, we started with two models. We derived these field equations from the geometry, then we went for the action. Then after that, we tested this FQLM gravity with two models. The first model is a linear model, and the second form is a nonlinear model. So in this linear form, so there are two parameters, alpha and beta. And here it is a square form, so the nonlinear form in the model B. And the matter Lagrangian we have considered are the pressure, which is gamma minus 1 into rho. If you take gamma is 1, then you can get the matter pole. And if you take gamma is 4 by 3, then one can get the radiation model. So both these matter and radiation model, you can obtain from this LM considering gamma is equal to 1 or gamma is equal to 4 by 3. Okay, so in these two models, these are the two Friedman equations. And first we check the, so if you go for this linear model, so what we saw in the linear model, the energy momentum tensor is conserved. So we got the conserved equation, so this gamma is 0 here. Where we just kept the gamma because it is not conserved, the balance equation. Okay, so what we did after that, so already yesterday Professor Suresh discussed about the Hubble tension. So he has showed various data sets what the present cosmology we used in the cosmological models. So in this article, we went for the statistical analysis, the MCMC analysis. So we consider the supernovae data and the Hubble data plus supernovae and biodata. So this is the combined data sets and this is the supernovae. So in the first model, the value for the H naught, we got 72.4 and 72.5 for the combined data sets. So these are the alpha beta, the model parameters, which we got from the 1 sigma and 2 sigma contour plots. Then if you go for this Q naught, so the values for the Q naught in the first model is coming to minus 0.44, and the transition from the deceleration to acceleration, which happens at 0.46 and 0.56. Okay. So coming to the second model, in the nonlinear model, so in the nonlinear model, the transition happens in 0.47 and 0.56, which Professor Swami yesterday told to Suresh that the transition should come between 5 to 6, 0.5 to 0.6. So exactly we are getting this transition in the combined data sets is 0.56 in both the models, in the linear model and the nonlinear model. And the values of the present deceleration parameter Q naught is coming at minus 0.44 and minus 0.48. So it is just similar results in both linear and nonlinear models. And the values of alpha, beta, gamma, as I mentioned, we used, we took from the 1 sigma and 2 sigma contour plots, the 68% accuracy. So these are the two contour plots for the linear model and the nonlinear model. Okay, so these contour plots gives us the values of H naught, alpha, beta, and gamma. Okay, now coming to the comparison. So what we did, we compare our statistical values with the chi-square and the AIC, BIC criteria. So As you see in the table, so generally the del IC and del VIC. So the del AIC and del VIC values for the lambda CDM model is 0. So the minimum values of the del IC and del VIC is always the more accurate towards the model. So in our model A and B, we got the del IC and del VIC values with 2.13 and 3.4. So 2.0. So it is the minimum values for the del IC. So it shows that our model is fitting to the lambda CDM. Now coming to the key parameters, particularly the density and the deceleration parameter and the equation of state parameter. So if you go for the density in both the models, so the rho bar is basically we have taken rho by 3h naught square. So the density you can see it is positive throughout the inverse. So the lower values to higher values of the z, and both then same in the second model. Now coming to the behavior of the deceleration model. So you can see the deceleration parameter. It has a transition from deceleration to acceleration, which approaches to lambda CDM, and this value 0.48 and 0.56 for both the Hubble data sets and the combined data sets. Similarly, in the second model also, there is a transition from deceleration to acceleration. Now coming to the equation of state parameter, the effective equation of state parameter omega. So in this case also you can see it is there in the acceleration phase, and it is approaching to the lambda CDM. Now what we did, so as I mentioned, we have discussed about the Klein-Jordan equation with the scalar field phi. So we have taken the mass of the scalar particles, and we discussed in both the models. So the effective mass square, where this initial mass square plus xi, and this, so this xi is the coupling parameter. So for this xi, the coupling parameter, we have taken the range of this xi, the coupling parameter, from -1 to 1. So you can see, so the bold line is for xi is equal to 0. So if we see when xi is negative, we are getting it is the values are coming negative for this effective mass square, and the values for xi when it is positive 0 to 1, you can get the positive value. So the similar behavior we are getting in both the models. So this is for the effective. So this is actually the effective mass square versus the initial mass in these two plots. And in the next plots, what we have taken the ratio of the effective mass square by initial mass square versus the redshift parameter z, and the z we have taken from -1 to 3, where the same the coupling parameter zeta is from -1 to 1. Here also you can get the same behavior when you go for zeta is negative, -1 to 0, you are getting this negative. So then this is the values for the positive zeta. Okay, then coming to the comparison of this model, our model with the lambda CDM model with the Hubble data set. So coming to the h of z versus z, so you can see our model is similar. So with the bold one is the lambda CDM model, the black line. Then this model A and model B are with the color lines. So it's, you can see this model is approaching to the lambda CDM with the comparison. Then in the next figure, we have taken the distance modulus, the mu of z. So the mu of z versus z, you can see the error bars and the comparison with the lambda CDM. Okay, so coming to the final remarks. So we have extended this general relativity to a modified non-metricity based gravity, which we named as FQLM gravity. Then we derived the FQLM field equations, and we calculated the tensor balance equation, then the modified Klein-Jordan equation, and the Friedmann equations. Then we solved the Klein-Jordan equations for both the models A and B, and we discussed about the effective mass square. Then solving the Friedmann equations for both the models A and B, we discussed the statistical analysis of the contour plots, taking the Hubble data sets and the combined Hubble, bio, and supernovae data sets. And what about the cosmological evolution through the deceleration parameter and effective equation of state parameter. So though the original paper is not published, there are extensions which are already published. So these are the two articles from in FQLM gravity which are already published in Physics of Dark Universe and Journal of High Energy Astrophysics. And there are 3 articles available in archive, which are the based upon the FQLM gravity and its extensions. So this is the present development by various authors in the literature. So now coming to the future, so one can go for the matter geometry coupling with various impacts. Then one can study the dark matter, neutron stars, photon rings, the Raychaudhuri equations. Then all the astrophysical objects like boson stars, Grava stars, the negative singularities, wormholes, one can study on this. So there are many things we can explore once this article is accepted in JCAP. So these are the collaborators. So the mostly the calculations as done by MSc students. So Ayush is a MSc student who came to me for internship, and Simran is my PhD student. She is a JSPS postdoctoral fellow at YITP now, and Professor Harko, who proposed FRT gravity, also mentored us in this FULM gravity. So these are the sources for the pictures, and these are some references. So thank you. So any comments and suggestions are always welcome, because this gravity we propose, which is not published, we can interpolate it.
Okay.
Yeah.
Questions?
I have a very basic question.
Yes.
So you have the Q, T, and LM. Right?
Yes.
So is there any motivation behind Q and LM, the combination, and why not the, like, we can have various combinations. So is there any like limitations or any?
Yeah.
Just
So
trying to understand.
basically, that is what I go 1 minute. Yeah. So if you go for this, okay. So generally based upon the Riemannian geometry, from GR the FR was started. Then from FR the coupling started, as I mentioned. The couplings are based on this matter Lagrangian. Then so this is the trace, the T trace of the energy momentum tensor, and the scalar field. Even if there is a article f of R, T, and R, so the combination of R mu nu and T mu nu. Okay. So these are basically the coupling. Then you can go for the linear form and nonlinear form to get the minimal and non-minimal coupling. So all the couplings are based upon the three things: trace, then the matter Lagrangian, and the scalar field. Okay. So the same thing you can get in the f of t and f of q. So f of qt is already there, which is proposed in 2021, and we extended the f of qt to f of qlm.
I see. Okay, understood. Thank you. And maybe if I can I ask one more?
Yeah.
So and then the model A and B.
Yes.
Again, like I'm just trying to understand the specific choice.
Yeah.
And then
So basically,
how they're
that's what
different.
I expect. That's what I kept I am not told that time. So if you go for these two models, so there are two model parameters, alpha and beta. Fine. So always there is a question, because this I used to get these questions why you have taken two model parameters, alpha and beta. Because the minimum of if you take minimum number of model parameter, it gives better result. So why you have taken two model parameters here? The idea of the two model parameter is, if you make alpha is 1 here, fine, then this will reduce to GR. Because I told that GR, we can get GR from minus Q plus LM, like beta will be. So what is the use of beta? Particularly beta gives a cosmological constant. We kept the beta to get the cosmological constant. Fine. So if you make alpha is 1, so this will reduce to GR, where beta will play the role of cosmological constant. Okay. So if you take Q is a function, right? Then you can get the FQ gravity. Okay. So then to get the linear and nonlinear models, so here we have taken LM and here we have taken the LM square. So we just want to check whether the model fits for both linear form and the nonlinear form. One can do another question. So here we have taken the linear of Q. One can go for the nonlinear of Q, because you want to get the FQ. So once you get, so this one, the first model, easily one can reduce to GR. So to get f of Q, so this Q can be considered as a function of Q. So if you go for function of q, then you can take some q square, q plus something, then take any functions of q, so that you try to reduce this model to fq gravity. In the first case, what we did, we tried to reduce these two models to gr, where beta plays a cosmological constant, and if alpha is 1, then it will go reduced to gr.
There are no more questions. Sorry.
Yeah.
Okay.
If
Okay, yeah, sure. So, is there any improvement for the nonlinear model B, like because, or it's just both of them fit the data well? It looks like.
this one.
Yeah.
Yeah, so that's what I told. So basically, what we take the nonlinear form in the matter-Lagrangian.
Mm-hmm.
Based upon the matter-Lagrangian, we have taken the nonlinear form. One can take on the Q. What you can make, you make Lm both the places, keep 2 Lm, and take Q1 Q square. So first model you can take Q, second model you can take Q square. So that you will get another nonlinear T where it is a function of Q. Right? And if you go for higher powers, then your differential equation will become more critical and getting a solution will be more complicated. So that case, then you have to go for solutions in numerical. You cannot get the exact solution, and you have to go for the numerical solutions. Because once you go for higher orders, then it gives difficult solutions.
Okay, let's thank Professor Sahu again.
Thank you.
So the next speaker is Sumanta Chakravarti, and has an interesting title, Tides, A Story of Love. So let's wait for his lovely talk.
Okay. So I guess very good afternoon because it is just past 12. Thanks to Sheshadri for chairing the session. Thanks to Professor Sami for inviting for this presentation. And thanks to Devottam and all the other organizers who have done a very good job here, arranging all the things pretty much smoothly. So first of all, I must apologize for being late. I did not attend the first 2 days because of some commitments at my home institution. And it is really good to come here again because I came for the first version of this conference at the CCSP, the center. So it is really nice to come up here once again. And again, I share a lot of sympathy and connection with this center because it was named after my PhD guide, Professor Thanu Padmanabhan. And as Daud said that the center and Paddy were very close to our heart. So what I'm going to talk today, unlike the previous talk, for example, the first talk was on Gauss-Bonnet, the previous talk was on some FQ gravity, and then we heard from Daud about some trajectories and quantum effects. This will be a purely classical gravity talk, but in general relativity. And I will try to show that there are still a few aspects in GR which are not well understood and worth exploring. And I found that it's a pretty cold day, so maybe many of you will be feeling a bit lazy and sleeping. So I use this buzzword, eternal buzzword, just to get you excited. But let us start without further ado. So just as you can realize from the outline itself that it is not really what you think it is. So this love is not coming from some word that you think. It is actually name of a British physicist, geophysicist to be particular, and who tried to calculate the effect of tides on various astrophysical objects. So that's why the name goes by tidal love number. Tidal come from tides, love is the name of that person. So what I'm going to discuss is these three things. So I will explain what they are: static and dynamic tidal love numbers for both black holes and reflective compact objects. So hopefully I will get there soon. So let us start with the description of tides. If some of you have been in one of my earlier talk, you may have listened a part of it. So I will take pardon from you and try to explain it to others. So suppose you look for, there are many students and also many faculties here. So for students, when you appear in a examination interview, and for faculties when you are interviewing the students, one question which is pretty commonly asked is what causes tides on Earth, right? So the answer would be moon causes the tide, but then the instructor, the interviewer says that look, but moon, the gravitational force is stronger due to the sun, of course. The Earth moves around the sun and not the moon. So therefore, why do you think tide is caused by the moon? So people can get confused at that time and say, no, tide is actually caused by sun. But then, gradually you realize, and maybe some of you will give the correct answer, that it's actually not the force, but rather the gradient of the force which causes the tide. And even though the force due to the moon is smaller, but the gradient of the force is larger, and as a consequence, it leads to tides. Now that is where the Einstein's theory also comes into play, because as you know, in Einstein's theory, metric, which is what we use to describe all these spacetimes, is like the potential in the Newtonian context, and derivative of the metric, which is like our Christoffel symbol or connection, can be set to 0 in any local inertial frame, that is the principle of equivalence, say for example. That means I can always set the gravitational force to be 0 at any point in space-time. But what really captures the effect of gravity is the derivative of the Christoffel symbol, or in other words, the Riemann curvature tensor. And the Riemann, if it is non-zero, then we definitely know there is gravity, because whatever coordinate you choose, how hard you try, you can never make the Riemann go away. And the Riemann, as I said, is the derivative of the force, because the force is the Christoffel. So therefore, tides actually capture the Riemann tensor which is present in our space-time. So non-zero tide definitely tells you there is a non-zero Riemann, and hence you live in a curved space-time. So that means understanding tidal properties can tell you about the nature of the gravity that we are living in, whether it is GR or some beyond GR theories and so on and so forth. There is also another effect that comes into play, which is the constituent of the matter. So for example, the Earth, which is mostly made out of water, 75%, if it is, instead of being water, made out of, say for example, orange juice, then of course the tides would be very different from what they are now. So that means if you are a distant civilization, you are looking at some planet and somehow you are able to find out what is the tidal properties of that planet, you can actually see a lot about the constituent of that planet. And that particular idea was used in the binary neutron star merger event that people have detected in the 2017 GW measurement. And from there you could constrain the equation of state of the neutron star by using exactly the same principle. That is, you measure the tidal deformation of that neutron star, which in turn lead you to comment on the constituent of the neutron star, and hence the equation of state of the same. So therefore, as the name suggests, that tidal effects are important in these two aspects. First, to tell you what is the constituent of the matter, and second, to tell you about the nature of the gravity. So the the simplest object that should come to your mind whenever you talk about gravity are black holes, because they are described by the least number of parameters, mass, charge, rotation if you prefer. And therefore, what about their deformation? Can they be deformed? What are their deformation? How to quantify them, and so on and so forth. Now, in the context of gravitational wave, of course, this is very important, because that's where you can see the tidal effects from large distances, like merger of black hole binaries or merger of binary neutron star. The only problem here is that, before going into the details, is that this effect appears at v by c to the power 10 order. So that means if your system is highly non-relativistic, like the early in-spiral phase when these two objects are moving around each other, then this effect is going to be suppressed until and unless the Love number or the deformation itself is very high. For neutron star, we know that this number is of the order of 700, and that's why you have seen it so well, because the number is very high. But even though it actually appears at a higher post-Newtonian or higher powers of v by c. And the other thing that I am going to discuss is what happens, if time permits, is what happens if an objects which are as compact as that of black hole, but nonetheless they are not black holes. That actually solves quite a few problems on a single go, because as you know, black holes are very good candidates. But if you have seen, this movie, Superman versus Batman, Dawn of Justice, I don't know if you have seen it. there is a famous saying, because I'm saying it in that way, is that it says that if you are all powerful, then you cannot be all good, and if you are all good, then you cannot be all powerful. So black hole is of course all powerful. It can, if you throw something into it, it takes everything in, it doesn't give anything out. So it is all powerful, but that means it cannot be all good. So black hole has three major problems. One is the existence of singularity, which it hides well beneath its horizon. Second is that existence of Cauchy horizon. As you know, we have rotating black holes in our universe, and these are the astrophysically relevant ones. And for any rotating black hole, there are Cauchy horizons beneath the event horizon. And the Cauchy horizon prohibits you for a deterministic evolution of an initial data, which is really problematic. And thirdly, you have the information loss paradox. People can say that there are solutions in various quantum gravity models, but I don't think they will agree with each other. So I will take it as an open problem as of now. So these three problems we do not have an answer to. But now you can actually get rid of all of them if you say that we really do not have a black hole, there is no horizon. I just have a compact object and it is slightly bigger than that of the event horizon. Then it solves all the problem. But as you know, there are no free lunch, so therefore there would be some bigger problems creeping other places, which I will come back to. And lastly, if again time permits, is that if this deformation depends on asymptotic properties of space-time, in the sense if we are talking about asymptotically flat Schwarzschild black hole or asymptotically non-flat Schwarzschild de Sitter black hole, if things change. So I will slightly take up my gear and go into the mathematical formulation. So let us talk about the Newtonian physics, where the idea and concept would be clear, and so that I can go to my relativistic context pretty soon. So first thing, as I mentioned, that the tidal field, which is Eij, it's a quadrupolar field over here, comes from double derivative of the potential. That's what I started saying, that you have a potential, first derivative is force, double derivative gives you tides. And you have two contributions to the potential, because in the Newtonian limit you have linearity of your equations, so the total potential adds up. So you have two objects, one say for example Earth and the Moon, so the total potential would be the potential of the Earth plus potential of the Moon. So that potential, as I said, comes from the metric, and effectively it is 1 minus dTt by 2 or 1 plus dTt by 2, depending on how you are writing it, as 1 plus 2 phi or 1 minus 2 phi. So it has two parts. The first line corresponds to the contribution due to deformation, and the second line comes from the potential arising out of the tidal field. So if there is no tidal field, forget that there is no Moon, for example, only Earth is present, and for this purpose you can take it to be static and spherically symmetric, then it would simply be a monopole term, which is m over r, and that's what you have over here, the first term. Then Moon comes in and deforms the Earth by the tidal forces. So therefore you have a quadrupole moment which would be generated, which is Qij, and you also have a contribution coming from the Moon, which just comes by integrating this equation. So in the sense that if you take double derivative of this potential, assuming Eij does not change too much over the radius of the Earth, then you sort of get exactly this result over there. So that means you have a cause and effect thing. So if you have Eij equal to 0, there is no Qij. If you bring in Eij, you have a non-zero Qij. So at least at the level of linear theory, for example, these two must be proportional to each other, because if one vanishes, the other also vanishes automatically. And this proportionality constant is what is called as the tidal love number. It sort of captures, given a tidal field, how much deformed is the object. This is dimensionful quantity lambda, because as you can see from here, Qij has a dimension of length cube, and Eij has a dimension of 1 by length cube. So therefore this lambda has a dimension of length to the power 5. Now you want dimensionless numbers, because in physics that's what matters. So what you do, you divide that by the radius to the power 5, because that's the only length scale that you have in your problem. If you are dealing with black hole, it would be the radius of the event horizon. If you are dealing with neutron star, it would be the radius of the neutron star. And that gives you this number K2, which should tell you everything about the deformation or tidal properties of the object. So now let us move on to the relativistic case. So in order to study the relativistic perturbation, we have to study perturbation of Einstein's field equations, right? In other sense, we have to start with a background metric G0 alpha beta and perturbed it by H alpha beta, which is my perturbation. Now H alpha beta will have 10 independent components because it's a a symmetric 4 by 4 matrix. We are in 4 dimension. So therefore, among those 10, you can actually decompose it into two parts, one which are parity even and one which are parity odd. 3 of them are parity odd and 7 of them are parity even. On top of that, you know that you have gauge freedom in your gravity theory in the sense that you have diffeomorphism invariance which corresponds to a vector field. So you can change your metric by grad alpha xi beta plus grad beta xi alpha, where xi is your diffeomorphism vector field. And a vector field has 4 components, and you can show that one of the component is parity odd and 3 are parity even. So using that, among those 3 parity odd components in H alpha beta, one can be killed by gate choice. So it brings to 2, and among those 7 in parity even sector, 3 can be killed, which brings it to 4. So that means if we are talking about the parity even sector, which is also referred to as the polar sector, you only have to concern about 4 components of the metric. So these are the 3 components. I will tell you where the 4th one is. The first one is the GTT perturbation, second is GRR, and this comes from theta theta and phi phi components. So delta G TT, delta G RR, delta G theta theta, and delta G phi phi. There is one additional part which is delta G TR, but that component vanishes because as you notice I am looking at static perturbation. There is no time dependent piece which is present here. In the static limit that does not contribute. Then you have 3 unknown functions and you can use Parter-Einstein's equation. The good thing is if you use the theta theta and phi phi components, you can show that H2 is H0, which is capital H, and that satisfies this differential equation, which has solutions in terms of associated Legendre polynomials, and these associated Legendre polynomial you can expand at infinity and at horizon. So you have a second order differential equation, so you must have 2 unknown coefficients C1 and C2 over here. The one thing that I would like to emphasize is that if you expand it at large distance, you can see C1 comes as a coefficient of 1 by r cube and C2 comes as the coefficient of r square. And this is precisely what we had here. The Qij comes as a coefficient of 1 by r cube and Eij comes as a coefficient of r square. So that means by a comparison, because at infinity Einstein's theory should go over to the Newtonian limit, so the C1 should capture your tidal deformation and C2 should capture the effect of the tidal field. And your tidal love number should be the ratio of C1 by C2. But now you have to determine that, what is that ratio. For that what you do, you say that my perturbation should be regular at the horizon of the black hole, which is expected because if the perturbation blows up then it is no longer a perturbation. So that's why this near horizon expansion also makes sense, and you can easily see looking at this particular term and this term over here that this H actually diverges when r goes to 2m, which is the location of the horizon, unless C1 is set to 0. So that means for the case of a Schwarzschild black hole, whatever be your external tidal field, the black hole cannot be deformed. So that's why the famous statement comes that Schwarzschild black hole has 0 tidal love number. You can show the same for Reissner-Nordstrom and also for slowly rotating Kerr black hole. But there was a lot of debate about what happens in the general rotating case. So there were some claim that it should be 0, some other people claim that it should be non-zero. So that's what I will concentrate in the next 15 minutes or so. So let us skip this. So let us come back to these questions that we wish to address. So first of all, as I said, there are these gauge ambiguities because some people calculated in some coordinate system found it to be 0, some other people calculated in some other coordinate system found it non-zero. So can we provide a formalism based on scalar? Then what happens in dynamical situations? Since I mentioned that this was only a static configuration that we are interested in, but that's not something that happens in nature. Like whenever these two black holes are moving around each other, it's a fully dynamical system. There is nothing which is kept static over there. So the question is, do black holes have vanishing dynamical tidal love numbers as well, which I think is a pretty important question to ask. And the last question I will come back to if I get time at the end. So let us start with the first thing. The first question was answered pretty recently in 2020 by these 2 groups, one from Latiek and Casals and the other one was from Shia. This group is from the France and the Shia is from Princeton. So what they tried to argue is that instead of working with this metric perturbation in some particular gauge, choosing some gauge choices, it is better to work with scalars. And what are these scalars? These are well known in the literature. These are the Newman-Penrose scalars, which have been used in solving the perturbation equations of curved black hole, for example. So if you see Teokolsky's paper, for example, they will have plenty of these quantities. So why these are important? Because if you take the psi0, which is one of the Newman-Penrose scalar, and sort of take the Newtonian limit, you see that it has a fall-off behavior which is r to the power minus 2l minus 1. If you put l equal to 2, it gives you 1 by r to the power 5. And this is precisely what we had in the Newtonian limit. You remember Qij had 1 by r cube and Eij has r square. So overall it has a 1 by r to the power 5 as the factor difference, which is also over here. So that means if you can solve for this quantity psi by whatever equations that you want, expand it at large distance, read off the coefficient of r to the minus 12 minus 1, that should immediately give you what is the tidal love number. This was the static case. The generalization to the frequency dependent case was pretty obvious from there. What you have to do, you have to compute this coefficient, take its real part, which gives you the love number. The imaginary part gives you something called the dissipation. So let me tell you the brief overview that people have learned from here. First is, you have to find out a differential equation for these Newman-Penrose scalars or wild scalars, whatever you want to put it, and these equations are known. These are known as Teokolsky equation. You have to solve these equations, and then after finding the solution, you just have to expand them at large r, asymptotic expansion. It's not strictly asymptotic, but we can come back to that later. And then you just read off the coefficient of r to the power minus 12 minus 1. It would be a complex number. You take its real part, that should give you the tidal love number or deformation that we are looking for, and the imaginary part gives you additional information, namely the dissipation in the system. So with that, Shia had tried to solve it. So this is the solution that you obtain. So as I said, starting point is the Teokolsky equation in some coordinate system. And then when you solve it, you can actually solve it in terms of hypergeometric function. And you then take the large r limit of it. The z quantity is nothing but r minus r plus, a rescaled radial coordinate. First thing is that for a black hole you need purely ingoing, because nothing comes out of the horizon, as I said. So that means this term over here, z to the minus 2ip plus, this is what gives you the outgoing mode at the horizon, which you do not want because your black hole is all absorbing. So you set this b equal to 0, and then you are just left with the first line of the solution. So you have the solution. Now what you have to do, you just have to expand it and find out what is the coefficient of 1 by r to the power 12 plus 1. So when you do that, expand psi4, you exactly see that the expansion involves a z is like r, because as I said, it is r minus r plus. So when r is very large, you can ignore r plus. So effectively it's a power of r. So r to the power minus 12 minus 1. So this guy over here, consisting of the gamma function, that should correspond to your response function. You should take its real part to give you the tidal love number. And here there is a note of caution, in the sense if you take L to be integer, this quantity can diverge, because gamma function of negative integers are generally divergent. So you have to do some manipulation, in the sense go to the complex plane and then simplify it and only put it to be integer at the very end. And what you get is this result. So you see it is purely imaginary. So using that, people argue that actually the tidal love number for any black hole in GR is identically 0, because this was done for the case of a curved black hole. But then what we realized in this particular paper is that this is not really true, because they had done some approximations which are not consistent with the scheme of the deriving the equations, for example. So when you correct those particular errors, you again get a similar expansion for psi4. So you can see this is r to the power minus 12 minus 1. This extra factor is present, but let us not comment on that for the moment being. But the response function changes to this quantity inside the curly bracket. First thing that we notice is that if you take the static limit of this solution, which means you take omega tending to 0, then your FLM is purely an imaginary quantity. So that means whether you talk about Reisner-Ostrom, Schwarzschild, Kerr-Newman, all of them will have vanishing static love number, and which is consistent with all the other results in literature. Sorry. Then we went on to compute what happens for the dynamical love number, and when omega is non-zero, and there again you have solutions in terms of the hypergeometric functions. Rest of the definition remains the same. but what you get is an FLM which is this, and if you take its real part, this time it is non-zero. Instead you get a result which goes as AM whole square and AM omega. First thing first, if you put A equal to 0, which is the Schwarzschild black hole, it identically vanishes. So the conclusion, Schwarzschild black hole, static love number 0, dynamical love number 0. Take slow rotation. Slow rotation means you ignore all terms of order A square. Again this term would be ignored. This is A into omega, which is again a second order term, so that is also ignored. So slow rotating black hole, love number is 0, static dynamic. You take axisymmetric tidal perturbation, which means you set M equal to 0. Then again, as you can easily see, the love number vanishes. It's only when you have a arbitrarily rotating black hole, then your tidal love number is non-zero for the dynamical case with non-axisymmetric perturbation, and that's what is in general. Like when these two objects are moving around each other, by no means there is axisymmetry, and by no means this is static, and most often these black holes would be rotating. So the conclusion is you have non-zero love number even for black holes in GR if it is rotating. We had also tried it for the case of an extremal black hole because that is also of interest to certain community. And there also what we found is that in the static limit the function is purely imaginary because 2L is an even number. So therefore the tidal love number vanishes. On the other hand, the response function has a real part. You can just calculate and show that this indeed, this is actually real over here. So again the conclusion remains that even for extremal black hole you have a non-trivial tidal love number. Now I think I have 5 minutes, can I have, or maybe 5 minutes, okay, great. So these I have already mentioned that why we should go beyond black holes, so let us not get into it. So this is a cartoon that one can have. So first of all, for a black hole you have a photon sphere, angular momentum barrier, whatever way you put it. Due to this barrier you see these black hole images, this M87 star or Sagittarius A star, all of this comes from this particular angular momentum barrier. The point is you can put another barrier over here which is quite far from that of the photon sphere but very close to that of the horizon, and there is some physics beneath it and you want to probe that. And what is the signature of that physics is that there is a non-zero reflectivity which is present. For black hole everything goes in, nothing comes out. Here of course things goes in, but there is also a part which comes out. So what we just wanted to see what happens to these objects and what happens to their tidal love numbers. Can these objects also be deformed with or without rotation? So what we found, let me go back to this slide. What we found is that if compact objects have non-zero reflectivity, then in general they can be deformed. And this is the formula for K2 that we obtained. So you can see it depends on the reflectivity, which is this quantity R1, and it also depends on where I have put the horizon, the surface. So therefore you have a star. So the way you should envisage this is that you have a star. The radius of this star is slightly larger than that of your horizon. So there is no horizon, just like for sun or neutron star there are no horizon. And this epsilon sort of characterizes the location of the surface of the star compared to the location of the event horizon. And the R1, as I said, comes from the reflectivity, and the most important part is the dominant contribution has to be 1 in order to get a non-zero love number. If it is anything different, then the love number actually vanishes in the static limit. So now let us go back to some of the plots here. So this plot shows how the love number changes with epsilon for various choices. As you can see here, it's the logarithmic dependence because the scale here is on the log scale, so it is more or less linearish kind of a fit. On the other hand, at this regime, you can see that this trend breaks down because this is where the reflectivity takes over. Since epsilon has become too large, so log epsilon is not that important. Similarly, you can plot it with frequency. So you can see from this plot only when your R0 is equal to 1, which is the case I mentioned, you have a non-zero result when frequency goes to 0. For all other cases, like whether R equal to 0, which is a black hole for which it's just a straight line. As I said, for Schwarzschild black hole, there is no tidal love number at any sector. But if your R0 is -1, then it goes to 0 and frequency vanishes. But then there is some non-zero, non-trivial oscillations which is present. One might be tempting to say that at higher frequencies this love number seemingly converges towards 0. But again, one should not delve too much into it because at high frequency our calculation may not be trustable because we are using a frequency expansion scheme for the computation. Now let me just point out to this very important feature that we noticed. First of all, the love number's value is pretty small, like 10 to the minus 3 for example over here. And as I mentioned, it comes as a coefficient of v by c to the power 5. So observing it with the present generation of detector can be really challenging. On the other hand, there are these places where the QNM frequency coincides with the frequency of this tidal field. So this is like a forced harmonic oscillator. So you have some object, you have a forced harmonic oscillator with a non-trivial frequency. If the characteristic frequency of your object matches with the frequency of the forcing term, then you know there are resonances which are present. Similarly here, the characteristic frequencies of these objects are also its quasi-normal modes as they are called. And whenever the frequency of the external tidal field matches with these modes, there would be resonances. And at those particular points, we can see that love numbers can be pretty high. We have sort of tamed it, but it can actually be pretty larger. So the hope is that if you have actually these exotic objects for which the frequencies are on the lower side, you can actually see them because there will be some frequencies where there will be high tidal deformation. How to see it physically? Like these two objects are moving with each other, you would see very little tidal deformation. Then suddenly, for some radius, the tidal deformation is going to be very high, and again it will come back to a small value. That will tell you that there is some resonance that it has hit, and possibly that can tell you about the existence of such objects as well. So I think with this I have finished my time, so I will come over to the conclusion. So as I said, non-rotating black holes have zero tidal love number. Whether you take static or dynamic, it doesn't matter. For rotating black hole, you have non-zero tidal love number in the dynamical case in general, because static is like a, it does not exist in nature, and everything is dynamical here. And tidal love number depends on asymptotics. This I did not get time to discuss because but I will flash the result. What we found that asymptotically de Sitter black holes have non-zero tidal love number, and it depends, it is actually proportional to the cosmological constant. So if you set lambda tending to 0, which is your flat black hole, your love number vanishes. But if you put in lambda, it seems to pick up that effect out of it. So if there is any question, I can go over to there. The love number of exotic compact objects, which are these star-like things, which are very close to that of the black hole. And as the name suggests, these are exotic, so that means with normal matter it is difficult to have them because they are going beyond the Book-Dal limit as it is known. Then they exist for very specific reflectivity, and there are resonances which are present. As I said, in general the observational prospect looks slim, at least with present generation. But with future generation, LISA, if you see it for a long duration, then maybe the dephasing will occur and give you some result which is not trivial. So with that, I thank all of you for your attention, and any questions would be very welcome.
Are love numbers useful for description of merging black holes or not?
Yeah, so
if you consider merge.
Sure. So love numbers are useful not during the merger phase, but in the inspiral phase mostly, because that's where these two objects are like, apart from each other and then influencing. While merging, the problem is it will be important because there would be tidal deformation, but that cannot be captured with this linear analysis. You have to do full numerical relativity. Now where this can be important is that normally in all the gravitational wave waveform models that people have considered in order to match with data, they all assume zero tidal love number for black hole, even the frequency dependent part. Now if the frequency dependent part is non-zero, and I think most of the people agree with what we have found, then it will suggest that the gravitational wave waveform itself should be modified in order to do the testing. The only downside, as I mentioned, is that the numbers are small. It's not that the love number is order 100 or order 1000, then we might have seen it already. But since the number is small, with LIGO it's very slim that we'll be able to see it. But if we can see it in LISA or DESIGO, say for a period of 1 year, 2 years or so on, so even if it is a small, it can be a repetitive effect because it's going to circle around many times, and hopefully then such effects can be observed. But yeah, that is, thanks. Sorry.
I especially find that interesting that it is a gauge independence description you did, the Neumann-Penrose variable. So I am asking that you talked mainly about black hole, rotating black hole and a d theta. I am saying that in the neutron star, Kentiagi has found some like I love Q relation, right? The so they probably use the linguist coordinate perturbation, not the Neumann-Penrose one. But I'm asking that could this be extended to the neutron star, something like I love Q? I mean the equation of state independent one. So could you just comment on that?
Sure. So I love Q relation, I mean, for the audience, generally tells you that the I, which is the moment of inertia of neutron star, and tidal love number, they are independent of the equation of state. But just to let you know that these are all done for static love numbers. There is no dynamics in it. That's first one. And second, for neutron star, I mean, you can calculate. These are all done in the context of metric perturbation theory, like the one I described in the first few slides, and not in Newman-Penrose formalism. But it really does not matter at that level, because we are only doing static calculation. For the dynamical calculation, that's where these things are going to become important, and people are now trying to find out what happens to the dynamical sector of the tidal love number, whether the universality is there or not. And we are also trying something similar, but hopefully.
So the T mu nu perturbation also you will take in the
absolutely, of course, of course.
Okay, so
of course.
What would be the decomposition of T mu nu? So just could you tell?
Okay, so in T mu nu, if you take it to be perfect fluid and isotropic, for example, then you will have three quantities. One is your rho, one is pressure, and the four velocity of the fluid, and the metric. Metric I have already told you how to part up. So rho you will part up, p also you will part up, but they are both scalar, so they will only contribute in the polar sector. The vector field, if you part up, the u mu, which is the fluid for velocity, there will be one part which will contribute to the axial sector, and some other part which will contribute to the polar. So the same decomposition goes through, and it can be worked out. Thanks. Sorry.
So can you tell us a bit more about the asymptotically d theta black holes?
Sure.
And then it's interesting how that the non-rotating black holes have zero, but then, I mean, you already like briefly mentioned, but then
yeah, so I will show you only two slides. I think that should settle the issue. One is this. So this is done for generic rotation, and as you can see, if you put a equal to 0, this goes to 0. Now I would tell this with a pinch of salt, in the sense that we have ignored terms of order omega square, and this is the calculation we are currently performing. The point is, if you keep terms of order omega square, what we are finding is that even Schwarzschild black hole will have non-zero tidal love number. But as I said, maybe next CCSP meeting or something we can discuss it. But as I said, it is preliminary, so I would not too much stress the result, because there are some other caveats which are also coming out of it. But just to answer your question, to linear order in frequency, non-rotating black hole doesn't have tidal love number. To answer the lambda part, so this is where the calculation is for Schwarzschild decider. I can very briefly go through it. So for Schwarzschild decider, this is your metric where h square is related to lambda. And you have two horizons, the event horizon, which goes to 2m when h goes to 0, and the cosmological horizon, which actually goes to infinity when h goes to 0. And then you can again solve the equation. Again, it is again hypergeometric function. I mean, in physics, almost everything is hypergeometric. And then you can find out what is KL2. So this is the result which we got. So you can see it is directly proportional to this h square. So if you set h tending to 0 limit, it identically vanishes. Otherwise, there is a non-zero contribution which comes out, which is a very small number. Observationally, it is not relevant, but just as a proof of principle, I think this tells you that asymptotics indeed will have some effect. Pardon me? Yeah, of course. This is the static part. So you can see there is no omega here. So it is a static love number. We have not calculated the omega part at all. Right? Thanks.
Any other question? If not, let us thank both the speakers
Thank you.
for the session, and we now break for lunch.
So the lunch is at usual place, and we'll resume our last plenary session.